Hello viewers, Rain City Wrench here. This video is going to be nothing but DSO pattern analysis using my Snap-on Veris Edge. I'm at home in the garage. I'm going to be using my own ride as a test vehicle. At the end of this video there will be a summary, so make sure you stick around for that. So let's get to it. Okay, let's get started. Today's test vehicle is my own personal ride. It's a 2002 GMC Yukon with the 5.3 liter in it. The first two patterns I'm going to show you are the ignition coil and one of the fuel injectors. One really nice feature on this Veris Edge, the Snap-on Zeus has the same feature, is this power standby mode. Just hibernates it. You press the power button and this light starts blinking. That lets you know you're in standby mode. It can go days in standby mode before it discharges your battery, and allows you to quickly boot it back up. Press it again. That way when you're testing multiple things throughout the course of the day, you don't have to charge it. It'll go all day unless you're using it like the entire day. All right, on the desktop, you hit this desktop button. You can take the desktop tabs off the bottom, and does a full screen, maximizes it for you. A couple of tabs up here. Scanner, we're not going to do any scanning, but if you go to scanner, this is vehicle specific. I don't have the scan module here at the house actually. It tells you to continue, and it goes in here, shows you some of the vehicles already looked at. We're not going to be doing any of that. That would be the look at your data PIDs, data stream, do bidirectional controls. That would be there. You hit your home button to go back. OBD direct is the same thing, but it's global OBD generic. If you want to do that, same thing. You'd need your scan module connected into your data link, which I don't have. All right, guided component tests. This has a plethora of information in here. If we go in and let's GMC 02 Yukon 5.3 VinZ. This will have all sorts of info. You go like the ECM. This will show you like where your module's located, the pinouts, the colors, the pin numbers. We're back probed in a coil and an injector, so this will show you how to back probe those. So let's go to fuel system, fuel injector, signature test. This shows a sample waveform right here. This also shows you the connector and where to connect in. I'm in B, the injector control signal. And if you want to hit view meter, it'll take this lower half of the screen and it will go into meter. We're not going to be doing any of that. If we come back out, we can go into ignition. Where's ignition? Ignition tests, primary, signature test. Same thing, shows you where to connect your connector and pins. Your IC control signal is C, then that's where we're at, or we're back probed into. Here's sample waveform. It's just an on-off square waveform. If you hit home, you can go back. So that's all in your guided component test. Got all sorts of cool information in there. We're going to go into scope. Now, when you're in scope, all your fast time events in like milliseconds, you're going to want to go in the lab scope. For all of your slower time frame stuff that you're going to graph over like 5, 10, 15, 20 seconds, you're going to go in your graphing multimeter. So quick time events, fast time events, where you got to capture something that is only in milliseconds, you're going to want to go in the lab scope, and that's where we're going to go. We're going to go 4-channel lab scope, and you can hear the module in the back here, scope module click. Now we already have trigger 1 is already going because you can see this little plus sign. So let's start this rig up and check some patterns. Now let's adjust our settings. One thing about scopes, they only know two things, and that's voltage and time. So if you're at a hospital and you're looking at an EKG, it's the same thing. Whatever input that they have connected to you, or whatever device they have connected to you, spits out a signal to the computer, and it's so when you look at the electrocardiogram for your heartbeat, it's voltage over time. So same thing. We're looking, all these patterns here are going to be voltage over time. So we are in 20 millisecond scale. You can see down here 20, so 0, 2, 4, 6. So let's adjust some settings here so we can get this entire pattern captured. We're at 20 volts. Well, we can take our channel 2 off. We're just in channel 1. So let's increase the voltage. So we're in 20 volt scale, 0 to 20. Let's go to like 50 volts. So you can see the flyback voltage is actually a little bit over 50 volts. So let's go to 100 volts. There it is. This is our signal. What it does, you can see battery voltage about 14 volts. Comes in the coil driver, or excuse me, the injector driver grounds it. This is the amount of time that it's spraying fuel right here. And that's about, oh, looks like my back probe's coming out a little bit. Push it in a little bit. There we go. Looks like it's about, 1.3, 1.4 milliseconds, because here's 6 milliseconds, there's 8. Oh no, it's like 2.4 milliseconds of on time, the amount it's spraying fuel. And then when it lets go of it, you have your flyback voltage, and then it comes back down and it repeats the cycle. And so this is in a 20 millisecond scale. We can change that. We can go to, let's go to 10. Now if I reach over here and increase the throttle, we're going to see the on time increase. It's going to want to spray more fuel. I probably better back out though and go with a longer event. Let's go back to 20 milliseconds. Let me see if I can reach over here and grab the throttle. Yeah, this thing still does have a throttle cable. It's old school. That's exactly what it does. So obviously this vehicle doesn't have any problems. It's my daily driver. This looks textbook. Now let's turn channel 1 off and let's look at our ignition coil. Now our ignition coil is on channel 2. What you do is you hit this little eyeball looking thing. Now you can see the patterns just kind of jumping around there. Well, our trigger event's still on trace 1. What we want to do is change our trigger. We want to go to trace 2. There we go. Now we're triggered on it. This little plus sign is green, so it means it's trigger number 2. I can pull it up there, but since it's out of my voltage range, bring it down here, and there it captures it. So let's change the voltage here. This one's out of scale. We're in 20 volts. This looks like it's only about a 5 volt signal. Go to 5 volts. There it is. It's actually like 4 a little over 4 volts. And I can move this pattern around. I can move it over here. So this is our ignition coil. Now this has a transistor in it, so it's different. What it does is sends voltage up, on, and then back off. And then everything else is handled inside the ignition coil versus other coils where it'll be 12 volts in and it'll pull it to ground and it'll release it to trigger it. This is exact opposite of that. Now when we increase the throttle, this won't change. And it does not. Now here's our slope. Our slope is pointing up, so it means it's going to capture the first event going up. We change our slope to down, and it's going to capture the first event going down. So let's change this. There it is. You can see our trigger is grabbing the first event to go down. Let's trigger it back up. It just changes it to the other side. And you can turn your filter on. We don't have to on this. And pull out a little bit of the noise. But that's a textbook ignition coil pattern for a GM, that is. And I think we could put both of them on here, although they're probably going to be quite a ways apart. What we'll do is turn channel 1 back on. And let's change the scale. We're on 20 milliseconds. Let's go to like 100 milliseconds. Maybe 200. There's 200. And here's the injector over here. Let's go ahead and trigger back on this injector. There we're on this injector. Now the time, or the voltage scale, it's 100 volts. Change that to 50. And let's grab up here on the top portion of it. Now let's stay down here. So within 200 milliseconds, let me think about this here. These are both on cylinder 1. So it's spraying fuel in here. Obviously this is the intake stroke, spraying fuel, and then this would be compression, top dead center or just a little bit before, and then that's going to spark and create your power event, your combustion event. That happens, you know, within, looks like 140 milliseconds, both of them. 500 milliseconds is a half of a second. So there's those two patterns. Obviously they look great, they better, because I don't want to have to be spending any money on this right now. Let's move on to some other tests. The next test I'm going to do is a starter current draw test. I'm going to use this high current amp clamp. It's my Mac Tools EM111. You can see the scale down here. The output is 1 millivolt equals 1 amp. Now starter inrush current can be over 500 amps, and once it overcomes inrush current, normal cranking amperage is probably between 100 and 150 amps. So I'm going to need to set the scale for 500 millivolts, since 1 millivolt equals 1 amp. And I'll show you that when we get into the scope. And it goes over here. I've got this on channel 2, the input, and I have channel 1 ground and that combined together. And I still have channel 1 connected in to my coil, because the test after that, we're going to use this trigger to do a relative compression test with my trigger on my #1 coil and this high current amp clamp. So let's get started. And I'm going to go back into scope multimeter. We're going to go into graphing multimeter this time. Volts DC. I have 2 channels turned on. We're going to turn off channel 1. And then look at our scale. We're on 5 volts. We need about 500 millivolts, since 1 millivolt equals 1 amp. And then we're on 5 second. That's probably pretty good. And then we want to turn on our amp clamp. We're going to go to 400 amp. You see the little input spike there. It's showing 16.8. We're going to use our zeroing wheel. Go to right around 0. And then we're going to connect it to the positive battery cable. That's where all the amperage is going to be going through. There's a smaller battery cable under here. It goes just to the junction box, but that's not the one we're concerned with. This is the main one that goes down to the starter on this vehicle. Let me put this back in my tripod. And I have the fuel pump relay pulled already. We're going to crank this over, so we are recording. Let's see what we capture. Well, this thing still wants to run. We'll save that. Still acts like it wants to start up. Don't want to do this too much and burn my starter out. And then we're gonna zoom out. Let's see what we captured in here. Just being sensitive, there we go. And I think my scale is a little too long. All right, there's the second time I cranked it over. See if you can see that good. All right, here's our inrush current. You can see it goes off the chart. It's a little over 500 amps to get this, to initially get this engine turning over, and it quickly drops down. It actually wanted to start right here. That's why and then it's pretty consistent, just cranking, because there's still a little bit of residual fuel in there. And so this is about somewhere in the 100 amp range right here. And that looks textbook. So if this was like 200 amps, 250 amps, there'd be a problem. You'd need to start running some voltage drop tests, or it might have a bad starter. And then all these little spikes here are all the compression events, and that's what we're going to check next. We're going to do a relative compression check by using this amp clamp. So let's do that one next. Now I'm going to want to turn channel 1 back on. We're going to use that as our trigger to know where number 1 cylinder is. And I think we'll go down to maybe like 200 millivolts. We don't need to capture the inrush current. We just need to capture the cranking events after the inrush. So 200 millivolts. And we're on 5 volt for ignition coil number 1. I think, yeah, that's where we need to be there. We're on 5-second scale. Let's go to maybe 1 second. Let's try this. This thing still wants to keep starting up. All right, let's save that. I think we got a pretty good pattern in there somewhere. Now I'm going back through my recording. Yeah, it looks like we got stored some good pattern here. That's pretty good right there. Okay, looks like, yeah, when I get all the way in there, you can see the trigger event for the coil, so that's where it would be firing at. So 1, 8, 4, 3, 6, 5, 7, 2. Yeah, and all these look nice and consistent. If one was lower than the others, or one didn't go up at all, then you would know that cylinder isn't contributing. It's a dead cylinder. It's losing compression somehow. So that's kind of a cool test. I don't use it a lot, but there you have it. The next test I'm going to do is to look at this fuel pump pattern. I've never looked at the fuel pump pattern on my own rig. I'm going to use this Mac Tools EM121 low current clamp. And this is 100 millivolts per amp. I already had the fuel pump relay out, so I just jumpered in using the leads out of my AES set. Now, I never did see a fuse in here for a fuel pump. It would have been much easier just to do that. I've got an adapter in my set for that, but I don't see it, so I went ahead and just jumpered my relay. And I know the power wire is pin 30, and that's what I'm going to stick my amp clamp around. We're going to turn this clamp on. We're going to go into scope multimeter again. And this we're going to do, we're going to go lab scope. We're looking at a quicker time event. We'll go low amps 20. So we're in 20, filters on, 20 milliseconds. Let's try that out. Let's actually make sure we're zeroed out. Yeah, we're pretty close. That'll work. We're going to put it around the wire pin 30. Start this thing up. There's the pattern the fuel pump's putting out. Looks like it's pulling about 8.5 amps. .4 amps on average, and here's the scale up here. So these are the brushes, the commutators, when the motor's spinning. And that's the pattern that we're looking at. Now I know on GM's 8.4 amps is pretty good. I've seen Vortex run like 9.5 amps, close to 10 amps. So this one seems to be in the ballpark. I know a couple Fords I checked, like Explorers, they're about, I think they're 5.5 amps. GM seem to run a little bit higher. But if this thing was pulling like, 10 amps, 12, 14 amps, like something like that, then I'd know we've got a problem. Probably got a pump going out. So that's our pattern there. You can see we're triggered. Triggered right there. Now, I'll show you one thing on this. When you go into low amps 20, it automatically moves the decimal point for you. So remember, we're about 8.5 amps. If we go back out, we go in the, what was it? Lab scope, volts DC. See here it's got 0.8, 0.9, 0.8471. So we'd need to move the decimal one. So instead of 0.84, so instead of 840 milliamps, it'd be 8.4 amps. When you go to low amps 20, it will automatically move the decimal, and there we are, 8.4 amps. And we can move this around a little bit if you want. This next test is going to be a parasitic drain test. Now I do this test all the time. This is my go-to test for checking parasitic drains. If a customer comes in and says their battery's going dead overnight or over the course of a couple days or a week, this is the test I use. Pretty much the only test I use. So I'm going to use this EM121 low current amp clamp again. Go ahead and turn it on. We're going to go into scope multimeter, graphing meter, low amps 20. We'll take the scale down to, let's say, 500 milliamps, half an amp. And then let's zero this thing out. You can see here it's about 12 to 18 milliamps. We're going to move this thumb wheel, get her pretty close. Anything under about 50 milliamps, I don't worry about anyway. You can have 20 to 50 milliamps as normal current draw. It's usually when you have like 2, 3, 4, 500 milliamps is when you have an issue or more. So let's connect this to the negative battery cable. Whoops, reverse it. Let's double check this one last time. Yeah, pretty close. And we have nothing, which we shouldn't. I've let this thing sit for about an hour. Everything looks like it's timed out. What I'm going to do is I'm going to introduce a current draw. I'm going to open up my little vanity mirror, see what that pulls. Whoa, that takes it off the scale. So what we want to do, we'll take this up to an amp. Maybe it's more than an amp. It's right around an amp. Oh, I turned something else on. So I've got 380 milliamps. Let me get you zoomed in here. So with this vanity mirror open on my driver's side, 380 milliamps. I might have woke up the BCM too. We'll shut it back down. Yeah, I think I woke the body control module up. So it's still pulling 240 milliamps. Before we didn't have anything. So it's probably woke up. Who knows how long it stays awake, maybe for a half an hour. Let's double check. I'm pretty sure I woke up a module. Yeah, there's 20 milliamps with the clamp off. We'll connect it back to the battery, the negative battery cable. And there we have 200 milliamps. So we're on, what are we on? 2 amp scale. Let's do this to 5 amps. And then I'm gonna plug my under hood light here on, or back in, see what that pulls. So now we're up to 1 amp. I'm plugging it back down to that 200 milliamp or 210. So this hood lamp's taking about 800 milliamps. Let me plug it back in. There, it's back on. But you can see how awesome this test is. That way you don't have to open anything up. You don't have to disconnect battery cables and wake up modules. It's just a really awesome test. Usually what I do is I prep cars. I'll make sure the battery is completely charged up. And then I'll make sure I've got usually the driver's window down, the door open, and I will go ahead and click the latch back close. That way I can get in and out of the vehicle without opening the door and waking up modules. So this thing still is drawn. I can open up that vanity mirror again. And there we're back up 360 milliamps. Let me open up my door. Let's see, we're on 5 amp. Let's open the door up. How much does that draw? That takes it off the scale. Let's go to 10 amps. So we're a little over 5 amps right there. So I've got, looks like all my interior lamps on. Let me shut the door, and you're gonna watch this body control module start turning lamps off here when they time out. It's on a delay. Okay, I heard it click off. We're back down to 300 milliamps. I suspect that body control module is still awake. It's looking for some stuff, and it'll probably take an hour or so to completely go to sleep. But that's just a fantastic test. I use this test all the time. That's how easy it is. Let's take this back down. We'll increase the sensitivity. We'll take this back down to 500 milliamps. And we're in a 20-second scale. There's 20 seconds, 0 to 20. And here's the 0 amps, down here the 0. So we're drawing somewhere around 260 milliamps. Oh, there's something. It went down a little bit. More like 250. Yeah, 245, 250 milliamps. If we take the scale out to like 2 minutes, see how slow it goes. And we can do a time event here. Let's take this back up to 10 amps. We're on 2 minute scale, or 2 minute time frame, excuse me. Then we'll open up the door again. Then we'll shut it. And it's going to turn these interior lights off there, turn the interior lights off. Let me plug this hood light in again. Yeah, it's just great to watch them in a graphing mode. So that's what I prefer. We're still drawing that 300 milliamps. Obviously, there's no problem with this vehicle. Now, let's say you got something that's drawing 500 milliamps. You go through your diagnostic procedure at that point. I usually I pull up the wiring diagram, a power distribution wiring diagram, and I work my way upstream. Usually it's at an underhood fuse panel, and then I eliminate it to which circuit and go from there. Since I have my low current probe still hooked up, let's see how many amps this alternator puts out, and let's take a look at the diode pattern on it. Let's fire this rig off. Okay, I've already got it on. We're going to go back into scope multimeter. This time, a diode pattern. We're going to want to look at it in a quicker time frame, so we're going to go into 4-channel. Well, we'll go into volts DC. Either one will work, or 4-channel. So let's connect this to the chargeback lead, and on this one, it's really easy to get to. It's just right here. We'll just hook it up. I've got my trigger already set. Let me get you zoomed in. And there's my diode pattern. Looks pretty good. And this is putting out, so it shows 4.68 amps, which would actually be 47 amps. So to keep this running, to do the ignition system, and I've got my, looks like headlights on, tail lights on, to run everything, it's pulling 47 amps right now. And then you can see the diode pattern in it too. It looks kind of like it looks almost identical to a fuel pump pattern, actually. If you see some nasty spikes on this, I saw a Dodge once, just sawtooth, big nasty spikes, and it had a bad diode pattern in the alternator. So this one looks great, and it's 47 amps. Let me show you real quickly. I was just playing around and turning on and off some various loads. So I have the headlights off, and we have 33.7 amps. Let me turn the headlights on. Now it goes to about 42.5, almost 43 amps. You turn the headlight off, back down to 33 amps. Let me turn the defroster on, the rear defroster. That brought it up to 49 amps. That's a big load. Let me turn it back off. Yeah, that's pretty neat. You can turn on and off different loads and watch it live right on the chargeback lead on the alternator. Okay, the last test I think I'm going to do with this clamp here is we'll look at the rear defroster. We'll see how much current that pulls. Same thing, I don't see a fuse in there for it. So I just jumpered it in, and I know it's pin 30 again. What we'll do is we'll just go around, put my clamp around 30. Make sure we're zeroed out again. I don't know how much this rear defroster is going to pull. We'll wrap that around that. Then let's change this back to 20 amps. It might pull more than 20 amps. Let me fire up the rig. Then I'll turn my rear defroster on. Oh yeah, that draws more than 20 amps. So what I need to do to capture this, so I'll go to volts DC, and then we'll take this to 50 volts. Well, there's 20 volts. Twenty-two 22.9 amps. That's actually what it's doing. So the decimals moved the decimal. This is 2.28, so it'd be 22.8 amps. So only need it 2.2, so 5 volt scale. 2.281, 22.81 amps. If I take this off, zeroed it out again, let's put it on my defroster. There we go. So if it runs off the 20 amp scale, you got to go back into volts DC graphing meter. If you want to get it above that 20 amp scale, you just got to move the decimal. So we're at 2.252 or 22.5 amps. Let me turn the rear defrost off. And then back on. There we go. That's a really quick test. Obviously, if it wasn't drawing any current, we got a problem and open. No power, bad fuse, or the grid, one of the grid tabs is broken off, or the grid's open. But obviously, this is working great. Next two patterns we're going to look at. One is we're going to sweep a throttle position sensor, and this one has old school cable, so I can just do it by hand. And then we'll check the pattern on this airflow meter. Let me put you back on the tripod. Let's get you in a little bit. Back in the scope multimeter. Let's check this TPS at first. So we're going to do a graphing meter. And we are already in there. You can see if we go out 4-channel graphing multimeter, we'll go to volts DC. And this is, what's this scale? 5 volt scale. Okay, I think this is 0 to 5 volt. Let me turn the key on to run. Should have about a half a volt, which we do, 0.56 volt. Whoop. Now let me go over here and sweep this TPS. I'm just going to open up the throttle all the way wide open and close it with my hand. There's wide open. back to wide open. I can just cycle it. What you want to do is see a nice flowing sweep. You want to see any glitches or any missing voltage in there. If you do, then that means you get a bad throttle position sensor. Great, well, my TPS is good too. Don't have to replace that. And then let's go over here. Let me start this thing up. Then we're going to go into lab scope for this airflow meter. We'll go into volts DC. Looks like we're already set up here pretty close. Yeah, 10 volts is pretty good. And we're on a 5 millisecond. This is a digital signal. And as I increase the RPM, I'm not sure if this will, well, I think it's a frequency change. All right, let's trigger this thing first. Trigger off a trace 2. So we can get a, yeah, there we go, more stable pattern. There's my trigger that just came in. And I'm going to go over here and accelerate, do a couple snap throttles. So that's what the computer needs to see to let it know how much air is flowing into the engine. So there's another pattern for you. Well, that one looks good too. The next patterns I'll be analyzing will be inside the vehicle here. I'm going to look at my J1850 communication network. Now this is an O2, so it's really old, and it doesn't have high-speed CAN. High-speed CAN would be on pins 6 and 14. I'm using my breakout box here. It's an AES Wave Line Spy. What this is an extension of your data link connector, and if you look, it actually has the shape of the data link connector, and all the pins are in the same spot. It was around 1996, I believe, when they went from OBD1 to OBD2, that the Society of Automotive Engineers mandated that all the manufacturers make one connector and designate certain pins for specific networks. So this J1850 is on pins 2 and 10, so it's high and low. Chassis ground's always on pin 4, signal ground's pin 5, your battery is always on pin 16, your ISO protocol here is on 7 and 15, and your CAN high and low are on 6 and 14. This would be a high-speed network, high and low. This vehicle does not have that. But we'll look at this J1850. We'll actually look at battery voltage and do a diode pattern check from inside the car here. Yeah, I hope this comes in. I got low light condition in here, so we'll see how this turns out. What we're going to do is go into scope again. Lab scope. We'll hit 4-channel scope. We've got channel 1 on. We'll turn channel 2 on. Looks like they're both in, or channel 1's 10 volts. Turn channel 2 into 10 volts. So let's see what we have. Turn the key on. Start this thing up. So you can see the lights blinking here on pins 2. That's the communication network. That's the modules talking on that line, and that's what I'm on. That's yellow channel 1. what we'll do is we'll kind of expand this a little bit. We're in 20 milliseconds. Channel 2 is down here on this negative. I've actually never looked at this older vehicle on the network on a scope. And I think these are single wire. The can highs are dual high and low, and they're a twisted pair. The wires are twisted and shielded. Okay, what do I do here? Let's move channel 2 up and out of the way and see what it looks like. So there it is. There's the communication network on this one. So what it is 0 volts, and then it's bits, it's talking, it pulses to around, it looks like 7 volts. It's 7 volts on and off. So that's how it communicates. Versus this can high and low, most of them that I know of, they are, the can high would be 2.5, and then it would go to 3.5 volts, and can low would be 2.5 to 1.5 volts, and that's how it talks, and they mirror each other. Now this channel 2, it is mirroring, but it's only like a 0 to 1 volt. Yeah, I don't know. Like I said, I've never looked at one of these before. These are almost obsolete now anyway. But hey, this is my rig. It's been paid for the last 15 years and still runs perfect, so I'm just gonna drive it till the tires come off of it. Or I shouldn't say that, drive it till the wheels come off of it. There's a saying for you. Okay, now we can go over here and look at battery voltage on pin 16. One other cool thing is if you just got your standard banana jack leads, you just plug right in. So what we'll need to do is change channel 2 to 20 volt scale. Move it down here, and there we go. We'll turn 1 off actually. And it's showing 14 volts, 14.18. I don't know if you can see that down there. And so that's what we're charging at. So you can check the charging system while sitting in here, just connected to your breakout box. Now we can check a diode pattern on this too. What we want to do is go to, let's see, it's been a while, down to like 500 millivolts. You'll turn your AC coupling on, filter on, and then we need to trigger this. So trigger trace 2. It triggers up out of it. There we go. Now there's the diode pattern. You can see it doesn't quite look as clean because we're picking it up here through all this equipment inside the vehicle. But you can actually check the charging system and the diode pattern while sitting inside the vehicle. There's with me accelerating. Yeah, so that's a kind of a cool check. One other thing I'll show you on these communication networks, turn back channel 1 back on, turn channel 2 off, and we'll turn the trigger back on trace 1. Watch when I shut the vehicle off. So it's still talking. Let me open up the door. shut it. So there it stops. I bet you if I push this key in or pull it out, it'll talk for a second, send a signal. There's pulling the key out, pushing the key back in. Now it stops. And let me show you when I open the door. Open it, sends a quick signal. Close it. There's a key on to run. And they're started up. But really cool checks you can do inside the vehicle. I mostly use this for looking at the ISO and CAN high and low. And what's nice about this breakout box too is you can quickly connect it in, and if your lights are on, these two green ones and the red one, most likely you've got a good power and good grounds. So let me talk about some pros and cons on this snap-on oscilloscope. This Veris Edge, from what I understand, is no longer going to be manufactured by Snap-on, or it may actually already be obsolete. They might not be making it anymore right now. And also, it has Windows 7, and Microsoft hasn't supported Windows 7, I believe, since January of 2020. So that's some things to think about. So this thing essentially is an obsolete unit. But all I needed to do is be a scanner and a scope, 4-channel scope. That's it. I don't need it to do anything else. I don't need any more updates. I've turned off my updates. It is the way it is. So if it keeps working the way it is right now for the next 5 to 6 years, I'll be completely content, and that's why I bought it. A couple of the cool features are the hibernation mode, like I've already talked about. Also, it has this stylus with a tether. It's really cool. The scope module is slim, this M4 module, and it's built into the back of it. It just slides in. Just pull the tab. The battery is right here. It has a camera and it has a kickstand, and it kind of has like handles here on the sides. Also, you pull this little flap. It's got micro SD, USB, charge adapter underneath this little flap right here. Yeah, so it's a really cool platform. The main reason I got it is, in the real world for me, seems like I'm underneath the dash on the passenger side, or on the driver's side, or on the seat, or underneath the hood, or in the back seat, or on the tailgate, or underneath the car. So it's a great platform, small, lightweight, easy to grab. Just push the button and you're ready to go. And it just made sense for me, so I went with it. Now, I bought this for $3,500 used from a retired tech out of Pennsylvania on eBay, and that seemed to be the going rate at the time. Who knows? I think maybe they're still going for that now. The Snap-on Zeuses are significantly more, like double that from what I've seen. So that's a few things to think about when you're buying these. If you don't have a scope and you're looking at getting one, I would recommend getting a 4-channel. I don't think you'll be happy with the 2-channel. Down the road, you'll wish you had just stepped up and got a 4-channel. And I guess my last word of advice, if you don't have a scope and you're looking at getting one and getting into doing oscilloscope testing, is when you pick one up, the best thing I can recommend for you is to use it, and use it on, like I'm doing right here, on cars that are working fine. And what you'll do is you'll get practice on the settings, and that way when you do need it, when you got a car that's got a parasitic drain or an issue or a drivability problem, you won't be fumbling around with the settings or not sure if you're getting the right reading. So the best thing you can do is to use it, and use it a lot. I try to use this thing a couple times a week, even if I don't really need to. And then sometimes when I really do need it, I may use it 4 or 5 times in a week. And so another thing too is when you get proficient at oscilloscopes, you'll be the guy in the shop that they'll be sending things to, versus you're not quite sure and then you're like, well, let's send this to the dealer, or you'll be sending it out to someone else. You'll be the guy that'll be sending all the hard, complex diagnostics and drivability stuff. So that's really cool. And you can maybe make some more money, who knows. So I hope you got some out of this video and liked it, and we'll see you in the next video.